Welcome back to Physics 192. I'm Gerard Blanchard. Last time we talked about electromagnetic induction, which means that when we have a changing magnetic field, a magnetic field that changes in time, that changing magnetic field induces an electromotive force or a voltage in a conducting loop of wire and also induces a current in that wire. Now, I'm going to do a demonstration of that for you. Here we have a solenoid. What a solenoid is just a bunch of wires wrapped around a cylinder. So they form a cylindrical shape. And so this is our solenoid. What that does is when we apply an electrical current and the electrical current circulates around the solenoid, if the current is circulating in this direction, then I would point my thumb in the direction that the current is going, and my fingers would show me that the magnetic field is entering the solenoid on this end. So the magnetic field must be coming out of this end and going into here. If I were to reverse the current, is that reverse? If I were to reverse the current and point my thumb in the direction of the reversed current, then the magnetic field would enter this end and come out of the top. So the north end of the solenoid, the direction that the magnetic field comes out, depends on the direction of the current. Now, I'm actually going to connect, or I have connected this solenoid to an alternating current source. This is our power supply right here, and it's connected to the alternating current supply that is in your house. And what that means is that the current will alternate 60 times every second. So it will turn this away, and then 1/120th of a second later, the current turns around, goes the other way. 1/120th of a second later, the current turns around this way. So as the current turns around and around and around and around, the magnetic field comes out and then back in, and then out, and then back in, and out, and back in. 60 times a second, it alternates up, down, up, down, up, down. So we have a changing magnetic field coming out of this solenoid. What I'm going to do is I'm going to take a conducting loop of wire. I have a circle of wire, and I have a light bulb connected to it so that when I induce a current, when that changing magnetic field induces a current in this wire, we can tell because it will light the light bulb. Let me demonstrate. Turn on, bring up our power, and now I will bring this coil of wire close to the alternating magnetic field, and you can see that we are lighting up that light bulb wirelessly. I'm applying power to the solenoid. The solenoid's magnetic field is changing, and that is transmitting power to the light. I can even feel the coil vibrating as the magnetic field changes. So what's happening is the magnetic field is going up, down, up, down, up, down, and that is inducing a current in the wire that is changing back and forth, and we're detecting that using the light bulb. So once again, I'm lighting up this light bulb wirelessly. This is actually the basis of all of our wireless technology. Your cell phone, your Wi-Fi, they all work, even radio, all work on this principle. We can even use this to send a signal wirelessly. For example, we could use Morse code, dot, dash, dot, dash. So we could communicate wirelessly using just this solenoid and this light bulb. We could also send digital data, 0, 1, 0, 1, 0, 1. And once again, that's how your cell phone works. That's how your Wi-Fi works. This is a pretty primitive version of it, but it all operates on the same principle that by changing a current in the solenoid, we're changing the magnetic field, and that can induce a response in other electronic devices. And what's actually going on here, we'll talk about this very shortly, is as the magnetic field reverses back and forth, we're actually sending out magnetic waves in all directions around this solenoid. What happens is we're going to send out closed loops of magnetic field that propagate out at the speed of light. So we're actually sending out radio waves, and it's the radio waves that we're intercepting that are lighting this light bulb. So one more time, just for effect's sake, as I turn on the power, I can light this light bulb wirelessly. This is also the basis if you have a wireless charger. That's also how wireless charging works. You can radiate energy through radio waves into your device. Now that we've seen why we're interested in electromagnetic induction, let's work some more examples. A long straight wire carrying a current I sub wire is in the plane of a circular loop of wire. The current I wire decreases from 0.75 amperes to 0.5 amperes in 0.33 seconds. The wire is 0.6 meters from the loop. The loop has resistance 24 ohms. The area of the loop is 0.01 square meters. In what direction does the induced current in the loop flow? And what is the magnitude of I sub loop, the induced current in the loop? Now, in this case, you can assume that the magnetic field through the loop, the magnetic field created by the wire that goes through the loop, is constant over the entire area of the loop. So you only have to find the magnetic field at the center of the loop, say. So draw your diagram, list all your knowns and unknowns, and get a head start working this exercise. Alrighty, let's draw our diagram. Here is our wire with I wire in it, and I will write I initial is equal to 0.75 amperes. I final is 0.5 amperes. And the change in time, delta t, is 0.33 seconds. So that would be t final minus t initial. And we have our loop. The area of the loop we're given is 0.01 square meters. The resistance of the loop is 24 ohms. And I believe that we have gotten everything out of the question statement. And the question is, what is I loop? Okay. Well, we know that I loop is going to be equal to the electromotive force induced in the loop by the changing magnetic field of the wire divided by the resistance of the loop. And we know the resistance of the loop, we just don't know the electromotive force induced in the loop. We do know that the electromotive force is equal to the absolute value of the change in magnetic flux over change in time. Let's go back to our diagram. This wire that has a current flowing in it is creating a magnetic field around it. I'm going to turn my page so I can show you the direction with my right hand. I'm going to lay my right thumb along the direction of the wire, and that means that my fingers will curl into the page on this side and around and out up here. So the magnetic field from this wire is into the page at this location. So this would be B wire. That is the magnetic field from the wire is into the page. Now, as B wire, as the current in this wire changes, B wire changes. It decreases. And that means that there will be an induced, according to Lenz's law, there will be an induced current in the loop that fights the change of the magnetic flux. So B wire, I'll turn my page around again. B wire is decreasing. B wire is decreasing, and so phi m is decreasing. So that means that we're going to have a current induced in this wire that supports B wire. The magnetic field from the current in the loop is going to be in the direction of B wire. Because B wire is decreasing, the induced current will support it. So in order to have a magnetic field that's into the page in this loop, I have to have a current that is clockwise. So if you imagine I grab that loop, put my thumb in the direction of the current, my fingers will curl into the loop on the inside and support that B wire. So I loop is clockwise. So I loop is clockwise. So that actually answers the first question. What is the direction of the induced current? And that is clockwise. So it is the change in the current in the wire that's changing the magnetic field through the loop, which is changing the magnetic flux through the loop. So the change in magnetic flux is due to a change in magnetic field strength. So I will use my expression for the change in flux that represents that. It is N times delta B over delta T. So NBA, the area of the loop is not changing, times the sine of the angle between the magnetic field and the plane of the loop. N is 1. Change in B, we're going to have to figure out. Change in time, we know. The area of the loop we're given. And the angle between the magnetic field, which is into the page, and the plane of the loop, which is the plane of the page, is 90 degrees. So E is equal to the absolute value of N, which is 1, times change in B, which is B final minus B initial, over change in time, which is 0.33 seconds, times the area, which is 0.01 square meters, times the sine of 90 degrees. And what we're left with looking for is B final and B initial, and we can calculate the magnetic field that this wire creates at this distance. There is one bit of information that I left out, and that is that the loop, the center of the loop, is at a radius r is equal to 0.6 meters from the wire. That's important. We need to know that to calculate the magnetic field, because the magnetic field decreases with increasing r. So we need to know exactly where the loop is. Okay, so if we can figure out B final and B initial, we'll be good to go with calculating E, and we'll be good to go with calculating the induced current. Okay. Make a space here to calculate that. B final is equal to mu naught I final over 2 pi r. And so that's equal to mu naught. Mu naught is 1.26 times 10 to the minus 6 times I final, which is 0.5 over 2 times pi times 0.6 meters. That tells us that B final is 1.26 times 10 to the minus 6 times 0.5 divided by parentheses 2 times pi times 0.6, and that gives me 1.67 times 10 to the minus 7 Tesla. So B final is 1.67 times 10 to the minus 7 Tesla. And similarly for B initial would be mu naught 1.26 times 10 to the minus 6 times I initial 0.75 amperes over 2 times pi times r, which is 0.6 meters. And that gives us B initial is the same thing. 1.26 times 10 to the minus 6 times 0.75 divided by parentheses 2 times pi times 0.6, and I get 2.51 times 10 to the minus 7 Tesla. So now we have B final, B initial. We've got everything we need to calculate E. So E is equal to absolute value of 1. I'm not going to write that. I'm going to write 1.67 times 10 to the minus 7 minus 2.51 times 10 to the minus 7 times 0.01, all divided by 0.33, and sine of 90 is also times 1, times sine of 9 is also times 1, so I'm not going to write that. And so E is equal to the absolute value of 1.67 times 10 to the minus 7 minus 2.51 times 10 to the minus 7 times 0.01 divided by 0.33, and that gives us negative 2.55 times 10 to the minus 9, or E, when we take the absolute value, is 2.55 times 10 to the minus 9 volts. That's the unit of electromotive force. And now I can come up here, and I loop is equal to 2.55 times 10 to the minus 9 divided by the resistance of 24 ohms. And so the current induced in the loop is equal to 2.55 times 10 to the minus 9 divided by 24, and I get a current of 9.25 times 10 to the minus 11 amperes. And that is what we were asked to find. And you can see that this is a tiny current, so this process is not very efficient, but it does work. As we saw in the preceding exercise, changing the current in one circuit can induce a voltage and a current in another circuit. This is referred to as mutual induction, and it's measured by capital M, which is the mutual inductance between the two circuits. So the long straight wire and the loop of wire have a mutual inductance, capital M, and mutual inductance has units of henries, Henries, and we symbolize that with a capital H. We'll see a lot of that later on. And the equation that M appears in is that E2, meaning the electromotive force induced in the second circuit, is equal to M times the change in current, delta I, in the first circuit divided by the change in time. So we could actually calculate the mutual inductance of the wire and the loop in the preceding exercise, because we did figure out the electromotive force induced in the loop of wire, that's E2, and we knew the change in current, I1, in the long wire, and we knew the change in time. So we know everything that we need to calculate the mutual inductance between the wire and the loop using this equation, E2 is equal to M times change in I1 over change in time. We're not going to do that, but we could do that. As we'll see in the following exercise, changing the current in any circuit induces a voltage in itself. This is referred to as self-induction and is measured by a capital L, which is called the inductance, which is also measured in units of Henry. And the equation in which the inductance appears is that the electromotive force in a circuit is equal to the self-inductance by the change in the current in that same circuit divided by change in time. And we'll see later when we talk about electrical circuits that inductance is very important, a very important property of electrical circuits. Now let's work an example in which we use that equation, E is equal to L delta I over delta T. A solenoid of length 2.8 centimeters and diameter 0.75 centimeters is wound with 160 turns per centimeter. The questions are, when the current through the solenoid is 0.1 amperes, what is the magnetic flux through the solenoid? When the current through the solenoid is 0.2 amperes, what is the magnetic flux through the solenoid? If the current in the solenoid increases from 0.1 amperes to 0.2 amperes in 5 seconds, what is the electromotive force induced in the solenoid? And then we get to the final question, which is the point of this exercise. What is the self-inductance L of the solenoid? Let's go ahead and draw a diagram, list your knowns and unknowns, and get a head start on this exercise, please. Okay, let's draw our diagram. Here's our cylinder. The diameter of the cylinder, D, is equal to 0.75 centimeters, so 0.0075 meters. So 0.01 would be 1 centimeter, and so we're 3/4 of that. The length of the solenoid is 2.8 centimeters, so 0.028 meters is the length of the solenoid. It is wrapped with 160 turns per centimeter. So the number of wraps divided by the length, the number of wraps per length is 160 turns per centimeter. 60 per centimeter. And I'm going to change that to meters. And by multiplying by 100 centimeters in 1 meter. And so that would be 16,000 per meter. So 16,000 wraps per meter. So we can solve this for N, and that should be L length that way. So the number of wraps is equal to 16,000 times L. So N over L is 16,000, so N is 16,000 times L, or the number of wraps is 16,000 times 0.028, or the number of wraps of wire is 16,000 times 0.028. That would be 448 wraps of wire. And we'll need to know that because our expression for the magnetic field of a solenoid, I'll go ahead and write that right here, B solenoid is equal to mu naught I times the number of wraps divided by the length. Okay. And what we have is that the current in the solenoid, I initial, is 0.1 amperes. I final is 0.2 amperes. Delta T is 5 seconds. And the first thing that we were asked for is, what is phi initial and phi final. What are phi initial and phi final? The magnetic flux initially and the magnetic flux finally. Well, we know that magnetic flux is equal to the magnetic flux is equal to the number of wraps of wire times B, the magnetic field through the loops, times the area, times the sine of the angle between the magnetic field and the face of the loop. Now what happens when we have a current that goes, let's say that we've wrapped these wires this way around the solenoid. So I'm going to grab the solenoid, stick my thumb, wrap my thumb around the cylinder in the direction of the current, and my fingers will enter this side and come out of this side. So the magnetic field of the solenoid is like this. It enters in this side and comes out of this side. And then, of course, it curves around and curves around the other way. So, but the angle between the magnetic field and the plane of the loops of wire is 90 degrees. So theta is going to be 90 degrees. We know N, B solenoid we get from this. The area we can calculate from the diameter of the solenoid. It's going to be pi r squared, or pi times d over 2 squared. So what we need to know is the magnetic field of the solenoid. We can calculate the initial and the final magnetic field. Let's go ahead and do that. B initial is equal to mu naught, which is 1.26 times 10 to the minus 6 times I initial. I initial is 0.1 amperes times the number of wraps of wire, 448, divided by the length of the solenoid, 0.028. So B initial is 1.26 times 10 to the minus 6 times 0.1 times 448 divided by 0.028, and that gives us 2.02 times 10 to the minus 3 Tesla. And B final would be the same thing. Oops, there we go. 2.02 times 10 to the minus 3. And B final will be the same thing. Mu naught I has changed. So N, L, and mu naught are the same. The only thing that changes is I final. So B final is 1.26 times 10 to the minus 6 times I final, which is 0.2 times 448 divided by 0.028. So B final is equal to 1.26 times 10 to the minus 6 times 0.2 times 448 divided by 0.028, and that gives us 4.03 times 10 to the minus 3 Tesla. And since we doubled the current, we should double the magnetic field, and we have done that within rounding error, and I just use that as a check to make sure that we did our calculations correctly. Okay, So we've calculated the initial and the final magnetic field. Let's calculate the initial and the final magnetic flux. Phi initial is equal to N, which is 448, times B initial in this case, that's phi initial, B initial is 2.02 times 10 to the minus 3 Tesla, times the area, which is going to be pi, times the radius squared, which is going to be 0.075 over 2 squared. So phi initial is equal to, when you do this calculation, be careful about your parentheses. You're going to have to divide the 0.075. Oops, actually I'm missing a 0. 0.0075. Because the diameter is 0.075. So your radius is 0.0075 divided by 2, and then we square that. So be careful with your parentheses. Then you multiply by pi and all the rest. Let's do that calculation. Phi initial is equal to 448 times 2.02 times 10 to the minus 3 times pi times parentheses 0.0075 divided by 2, and then I'm going to square what's in the parentheses, and I come up with 4.00 times 10 to the minus 5 Teslas times meter squared, which are actually Webers. Webers are the units of magnetic flux. So 4.00 times 10 to the minus 5 Webers. Now we'll do the same calculation for phi final. Once again, since the magnetic field is doubled, we should have twice the magnetic flux, but let's just calculate it as a cross-check. Phi final is equal to 448 times 4.03 times 10 to the minus 3 times pi times 0.0075 over 2 squared, pi r squared. Phi final is equal to 448 times 448 times 4.03 times 10 to the minus 3 times pi times parentheses 0.0075 divided by 2 quantity squared, and I get 7.98 times 10 to the minus 5 Webers. 7.98 times 10 to the minus 5 Webers, which is almost exactly double that number. So our cross-check works. And we've answered the question, the intermediate questions of what is the flux through the solenoid initially, what is the flux through the solenoid finally. Our next question is, what is the electromotive force induced in the solenoid? Okay. The electromotive force is equal to the absolute value of the change in the magnetic flux over the change in time. So that would be the absolute value of phi final minus phi initial over delta t. So that would be the absolute value of 7.98 times 10 to the minus 5 minus 4.00 times 10 to the minus 5 divided by the change in time, which was 5 seconds. And so the electromotive force is 7.98 times 10 to the minus 5 minus 4.00 times 10 to the minus 5, all of that divided by 5, and that would be 7.96 times 10 to the minus 6. 7.96 times 10 to the minus 6 volts. And that is the answer to the third intermediate question. What is the electromotive force self-induced in the solenoid when this happens? And it is 7.96 times 10 to the minus 6 volts. And the final question was, what is the self-inductance of the solenoid? And for that, we use our equation. The induced EMF is equal to L times the change in current over change in time, where we're looking for L. So I will solve for L, and I will say the electromotive force times delta T divided by delta I is equal to L. The electromotive force is 7.96 times 10 to the minus 6. Delta T is 5 seconds. And the change in current is 0.2 amperes minus 0.1 amperes. That's I final minus I initial. That's equal to L. And let's go ahead and do our calculation. 7.96 times 10 to the minus 6 times 5 divided by the quantity 0.2 minus 0.1 gives us 3.98 times 10 to the minus 4 is equal to L. And the units of inductance are henries, H, and that answers the question. What is the self-inductance of this solenoid? The self-inductance of this solenoid, or in other words, a solenoid with this diameter, this length, and this many wraps of wire. So that's what the self-inductance depends on. It depends on the length, the diameter, and the number of wraps of wire. The self-inductance of that solenoid is 3.98 times 10 to the minus 4 henries. So that is electromagnetic induction. And as I hinted at earlier, electromagnetic induction plays a big role in electromagnetic waves. As I said, our solenoid, as the magnetic field reverses back and forth, it gives off electromagnetic waves, actually radio waves. Microwaves and light are also electromagnetic waves. So we've reached a point in our course where we're going to transition from electric charges and currents and electric and magnetic fields into optics. We'll start with that next time. Until then, think physics.